this is supposed to be mathematical physics. And as you know, there are different styles of doing mathematical physics. One style is a very rigorous approach, very, very rigorous, where it's all theorem and proof. And I personally find that less interesting. Okay, let's be polite. So I don't like theorem and proof type approaches to doing physics, especially mathematics that's going to be used in physics. And I prefer to talk about what I regard as really useful and powerful mathematical techniques. And a lot of what I'm going to be telling you is, in fact, not rigorous, at least not rigorous yet. And because of that, it is more powerful. Okay, so the more rigorous you get, in fact, the less powerful you are. And that's because the more general you are and the more rigorous you are, the less you can use it to solve new problems. Okay, proving general theorems is often not very useful. And I'm going to be showing you how to solve problems, the kind of problems that you're going to encounter in physics. And that's going to be the purpose of this course. So what I would like to do is to develop the kind of mathematics that you need to solve very, very, very difficult problems. Okay, that's the objective here. I don't know how much I'm going to cover, and that kind of depends on how interested you are and how fast we can go. And I know how successful I am because I can look at you while I teach. And if I see you drifting off, then I'll have to go slowly. And if I see that you're following me, then we can go faster. Okay. So let me begin by giving you a sort of partial outline of my course. That is an outline, I guess, of this course. Why do the lights keep going down? That's it.
You just have to say the word.
Yes, you just say, turn up the lights. Okay, so what I want to begin with is talking to you about perturbation theory. If you have a very hard problem to solve, in fact, let me put it this way. If you take most courses in undergraduate or graduate school, they tend to concentrate on problems that you can solve exactly. And it's very nice when you have a problem that you can solve exactly, but almost no problems are exactly solvable. That's the problem. That's why it's difficult. And all the exactly solvable problems, and there are about 3 or 4 of them, that's all, have already been solved, unfortunately. And all the rest of the interesting problems that need to be solved cannot be solved exactly. And you're going to need to have tools for solving what I will call, generically, a hard problem. Okay, let's see. This is an attack stick. Okay, so this is what we're going to try to talk about, hard problems and how you can solve them. Okay, and there are basically only 2 approaches. Either you can use numerical methods, and this is not a course on numerical methods. Okay, so one possibility is that you can use numerical methods. I don't trust most numerical calculations because I tend to think of them as being like a sausage. They're just fine until you find out what went into them. But what we want to talk about here is analytical approaches to very, very hard problems. Okay? And there is one standard analytical approach, really only one, and that's called perturbation theory. And most people, when they hear the word perturbation theory, they begin to get bored. In fact, perturbation theory is amazing. I'm going to show you that is truly an amazing technique. And it is very powerful, very beautiful, and it reveals all kinds of remarkable stuff about quantum mechanics. So let's begin with a discussion of, how do you approach a hard problem, one that you can't solve exactly? Well, there are always 3 steps when you do perturbation theory. And the first step, so here is a hard problem, okay? The first step is to insert a small parameter epsilon into the problem, okay? So instead of solving one hard problem, amazingly, now we're solving an infinite number of hard problems that depend on a parameter epsilon. It's hard to believe. You can't solve one problem, so instead you convert it into an infinite number of problems, one for each value of epsilon. That doesn't sound like progress, but it is. You'll see. The second step, and this is a very tricky and very subtle idea, is to assume that the answer to the hard problem, which of course depends on epsilon, because there's one answer for each value of epsilon, we can assume that the answer has the form of a perturbation series, okay? Okay, that's a perturbation series. Now, in fact, I have assumed that it is a Taylor-like series, and in general, it isn't always a Taylor-like series. But for now, let's assume that the perturbation series is in a Taylor form, okay, a sub n epsilon to the n. And the objective now is to calculate the coefficients in the series, okay? So we calculate a0 and a1 and a2, and if you're a professor of mathematical physics, you could probably calculate that much. If you're a graduate student, you could probably calculate a few more because you're willing to work harder. And if you're an undergraduate student, and if you're in high school, you can calculate lots of coefficients. And now we have the many terms, maybe even an infinite number of terms, if you're lucky, in the perturbation series. And now what do? Well, the answer is you add up the series and you calculate the answer. Okay? And every one of these steps is really interesting. It can be very subtle and very tricky, and it requires a lot of art, a lot of interesting mathematics. But the basic question is, why does this procedure work? If it works, why does it work? The answer is that you begin with an extremely hard problem, and you reduce an infinitely hard problem to an infinite sequence of very easy problems, or let's say relatively easy problems, okay? Because instead of trying to get the whole answer in one shot, now you calculate a little bit of the answer and a little bit more and a little bit more and a little bit more and so on, and you get the complete answer to the problem. You add up the series, and then at the end, you set epsilon equal 1, and that's the final answer to the problem. Okay, that's the outline. Okay, so let's make up an interesting problem to solve. And let's see how powerful this tool really is. So what's a hard problem? Well, how about solving this equation? Okay. Why is that a hard? Do you know why that's a hard problem? I mean, why do I classify this as a hard problem? Do you know why?
There's no closed form solution.
That's right. That's right. You know from high school, or junior high school, quadratic formula for quadratic equations, and there is some other formula. Do you know? For cubic equations. Cartons. You can write down an exact solution to a cubic equation. Same with a quartic equation, but that's it, no more. So I wrote down a quintic equation, and you can't write down the answer. So by definition, this is not an exactly solvable problem. You can't write down the answer. Okay, now suppose your problem is to find the real root of this. By the way, what do you think the answer is going to be? I mean, roughly. Can you guess? If we're looking for the real root. The problem is to find, the real root.
0.92.
No, not that big.
Not that big.
Think about it. You have a number, which you're adding to another number, and you're getting 1. There's a positive root. It's about 0.7, roughly 755, something like that. Okay? Okay, you can just make a plot. Draw x to the 5, draw x, add this to this, and ask where does it cross 1, right? And it's going to be about 7, it's about 3/4, something like that. Okay, so we say, fine, we know we can't solve this problem exactly. Let's try to use perturbation theory. So step 1, we have to insert an epsilon. Now this requires a lot of art and a lot of cleverness because there are lots of places where I can put an epsilon. Okay? There are many possible places to put in an epsilon. Let's take one possibility. Let's put it over here. Okay? Now, if you are doing, have you had any quantum field theory yet? You've had some exposure. So, can you say what it is that I just did? This is a strong coupling expansion. If you had a quantum field theory where the Lagrangian or the Hamiltonian was something like grad phi squared plus m squared phi squared plus, say, phi to the 4. Have you seen things like this? Okay. So you have some coupling constant over here, okay? And we could treat this as epsilon. That would be called the weak coupling expansion. Or, in other words, we could put the small parameter in front of the highest power. Okay, in this case, it's 5. Or we could put a small parameter in front of the lower power, which in this case is just 1. Okay, so this is called a strong coupling expansion. But never mind, that's just words. It doesn't have any. Okay, great. So now we've finished step 1. Now, there's one thing that's very important about step 1 that I haven't explained to you yet. When we put the epsilon into the problem, we have to put it in such a way that when epsilon is equal to 0, we can solve the problem. Because that, when epsilon is equal to 0, that's the unperturbed problem. Okay? And it better be that that's a problem we can solve exactly. Okay? So epsilon equals 0 is the unperturbed problem. And we have to be able to solve that problem exactly. Can we solve that problem? Well, if you set epsilon equals 0, you get the equation x to the 5 equals 1. And yes, I can solve that problem exactly. And if we're looking for the real root, I see that the answer is x equals 1. Okay? So that's actually not bad. I mean, you know, as things go, if we were doing astrophysics or something, you know, if the answer is 3/4 and we get 1, well, it's not bad. You know? I mean, if 23% of the universe is dark matter and we come up with, say, 18% or 30%, that's pretty good. Okay, good. So we have solved the unperturbed problem. Okay. So that's as much as we can say about step 1. And by the way, what is this 1? What is this 1 going to be? That is precisely the first term in this perturbation series. You understand that? So we have replaced one problem by an infinite number of problems. Okay? But now we're going to look for an answer. Here's step 2. We're going to look for an answer in the form of a series like this. So the first term in the series is 1, because that's what you get for epsilon equals 0. And then we have A epsilon plus B epsilon squared plus C epsilon cubed, and so on, like that. Okay, great. Okay, so now the next thing we have to do is to try to calculate these coefficients in the perturbation series. Okay, so how are we going to do that? Well, what we have is this equation here, and what we have to do is to substitute this series into that equation. And there's one technical problem, and that is, how do we raise this series to the 5th power? Okay, so let's just do a side calc. Can everybody see if I work over here?
Yeah.
Okay, so the question is, how do we raise 1 plus something, s or something, to the 5th power? Okay, well, the first term is 1, and then we have 5 times that something, plus 10. All right, 10 times that something squared, and so on. Okay, so if this something is A epsilon plus B epsilon squared plus C epsilon cubed, and so on, then 1 plus that something to the 5th power is 1 plus 5 times all of this, right, which is 5A epsilon plus 5B epsilon squared plus 5C epsilon cubed, and so on. And then we have plus 10 times the square of that. Okay? So if you square that guy, what do you get? Well, first we'll square this term, and you get A squared epsilon squared. Right? And then you get 2AB epsilon cubed, and more terms, and I'm tired already. Okay? So if you write this out, you get 1 plus 5A epsilon plus epsilon squared, and there are 2 terms. There is a 5B plus a 10A squared. Okay? And I don't know whether we have the strength to keep going, but maybe. Okay, then we have 5C, we have epsilon cubed times 5C, and then plus 20AB. Okay, great. So now, this is the technical part of the calculation. It's kind of boring, but let's go ahead and do it. So this equation here, the one we're trying to solve, says that 1 is equal to, first, we have this x to the 5 term. 1 plus 5a epsilon plus epsilon squared 5b plus 10a squared plus epsilon cubed 5c plus 20ab. Okay, and then we have epsilon times x. Okay, so epsilon times this series is just epsilon plus epsilon squared a plus epsilon cubed b. And you can see that this is very long and messy and busy, but this is trivial, okay? I mean, you can do this if you're in junior high school. Okay? This is not hard. Now, what do we do next? The left-hand side is a series in powers of epsilon. The right-hand side, well, that's a series in powers of epsilon too, but all the coefficients in the series are 0 except for the first one. What am I going to do?
Equate the coefficients.
Right. What right have you got to do that? Why is it true that the coefficients on the right-hand side have to agree with each power of epsilon, have to agree with the coefficients on the left-hand side? Why is that true?
Well, on one thing, I could put everything on the left-hand side.
Sure,
Equate them
you
to
could do
zero.
that and then equate them to 0. But why does it have to be, why does it have to vanish term by term?
It's
Because we have not
true for any
defined
of
epsilon yet.
Well, it's because Taylor series are unique. Okay, so given a function, the Taylor coefficients of that function are unique. What assumption am I making here?
So this converges.
Right. This is a very deep and interesting assumption, because in order to make a statement like that, with the mathematics that you know from first year calculus, basically, you have to know that the series converges. We don't know that the series converges because we don't know what the series is yet. So that's why I love to do non-rigorous mathematics. We're exploring this problem. Maybe we'll find, to our delight, that the series really does converge, but we don't know it yet. So we're proceeding boldly, okay? Now, term by term, they have to agree. So what's the coefficient of epsilon to the 0 power? Well, that gives me the equation 1 is equal to 1. It's a very difficult equation, and it's a true equation, okay? And that's true because we already did this calculation to 0th order in perturbation theory. We solved the unperturbed problem. Okay, now, what about epsilon to the 1st power? That gives me the equation 5a, okay, there's an epsilon, plus 1 over here, because there's an epsilon, is equal to 0. Now, you remember what I told you. We do perturbation theory because it reduces a hard problem to a sequence of trivial problems. That problem is pretty trivial. You have to agree. This is a pretty trivial problem, okay? What about the coefficient of epsilon squared? Here's an epsilon squared. So that says 5b plus 10a squared, okay? And here's an epsilon squared plus a is equal to 0. Now this problem is a little bit messier than this problem, but you have to agree that this is in the category of trivial, okay? In fact, if we solve this problem, you get a is equal to minus 1/5, and if you solve this problem, you just plug in a, okay? So we have 5b plus 10a squared, which is 2/5, plus a, which is minus 1/5, is equal to 0. So 5b plus 1/5 equals 0. b is equal to minus 1/25. Okay? And I picked this problem because without bothering to waste your time to calculate the coefficient of epsilon cubed, well, let me give you an IQ test. 1/5, or minus 1/5, minus 1/25. Can you guess what C is? Very good. Okay, great. So now we have this term, and this term, and this term. So we now know, that was just the technical calculation, but let's write the answer down. We now know that the answer is a series that begins 1 minus 1/5 epsilon minus 1/25, epsilon squared minus 1/125, epsilon cubed. Okay, that's pretty cool. We finished step 2. There it is. That's the end of step 2. We have found the perturbation series. And what I said before is really true. If you were in high school, you could calculate lots of these terms because you'd find this interesting. Okay, by now you find it dull. Okay, but there we go. Now the question is, how do we do step 3? Step 3 says you have to add up the perturbation series with epsilon equals 1. Okay, so we set epsilon equal 1. So this is step 3. We set epsilon equal 1. And the perturbation series, this is the answer at epsilon equals 1. Perturbation series has the form 1 minus 1/5 minus 1/25 minus 125, and so on, which is 1 minus 0.2 minus 0.04 minus 0.008, right? Which is 1 minus 0.248, which is 0.752. Okay? That's the answer that we get, 0.752 so far. Okay? And the correct answer is 0.755. Okay? So with that amount of work, which is really trivial amount of work, very lowbrow, we're off by 3 parts. The error is 3 parts in about 750, okay, which is a fraction of a percent. So we did a very small amount of work, and we got a very good answer. We didn't get the exact answer, and we know that we can't get the exact answer. We know we can't do that. But we did get a very accurate answer, and if we do more work, we get paid for it. The answer gets more and more and more accurate. Okay? So again, why do we do perturbation theory? Because it takes a very, very hard problem, this very hard problem, and reduces it to an infinite sequence of easy problems, and we solve them one at a time, and we get an answer that becomes increasingly accurate as we do more and more work. Okay? That's what this course is going to be about. Now, this is deceptively simple. This is really simple. For example, let's begin. Can you tell me, you guessed the 1 over 125. Can you tell me the next term?
I think it should be positive. At some point, this has to rise up again.
You're absolutely right. Whoops, how do we, wait, let's move up. Okay. So the next term happens to be 0. It's not as simple as you think. However, if there are people here who like to solve interesting problems, in fact, you can find a formula. You can guess, just by calculating a bunch of terms in that perturbation series, you can guess a formula. Great, thank you. You can guess a formula for the nth term. Okay, now I'm going to show you some more terms in the series. This is the problem that we've been talking about, and here is the exact answer. You know, you can put it on a computer, find the exact answer. This is the problem that we solved, and if you want to go through the trouble, this is what the sequence of easy problems looks like. This is what the coefficients look like. Okay? It turns out the 4th coefficient is 0. But as you guessed, eventually you're going to have some positive contributions, and you will have several positive contributions, and then another 0, and then several more negative contributions, and then another 0, and so on. And it'll happen like that. And if you sum up the series, you will find a very, very, very accurate calculation of the exact answer. Okay? And in fact, there is a formula you can guess if you like to pass IQ tests where you guess the next number in the sequence. There is a formula for these numbers, and you can guess it if you just play. And if you look hard at those numbers, you can guess what the radius of convergence of the perturbation series is. And the radius of convergence is 1.649. Okay, now that's very, very good, and it's very lucky, because we were putting in epsilon equals 1. So apparently, epsilon equals 1 is inside the radius of convergence of the series. Okay? However, what if you were trying to solve the hard problem that looked like that? Okay? You would do exactly the same thing, except at the end of it, you'd replace 2 by epsilon, right? And at the end of the calculation, you would try to set epsilon equals 2, but now you'd have a problem, wouldn't you? So in fact, one of the subtle things in perturbation theory is this step. You might think that the first two steps are the subtle steps, but the really subtle and interesting step in doing perturbation theory is step number 3. That is plugging in the value of epsilon and getting the right answer. And one of the things I'm going to teach you in this course is that when you have a divergent series, it's not an obstacle. I'm going to explain to you how to sum a series that diverges and how to obtain the correct finite answer from a divergent series. And in doing this, we're going to have to develop a new kind of mathematics, because the kind of mathematics that you've been taught until now is exact mathematics. Okay? It is the mathematics of equal signs. And this is a problem, because this mathematics is very limited in power. And what we're going to do is replace this mathematics by what is called asymptotics. Instead of exact mathematics, we're going to be doing asymptotics, and we're going to replace the equal sign by that symbol. And this is a much more powerful kind of mathematics because it is not exactly correct. Okay? So it's going to be far more powerful. Of course, when I say it's not exactly right, I want to emphasize that it is arbitrarily accurate. So there's a difference between saying that f is equal to g. This means f is exactly equal to g. There's no difference between f and g, none whatsoever. Or when I write down an equation like this, f is asymptotic to g, that means that f comes arbitrarily close to g without actually being equal to g. Okay, now you may think, what's the difference? And it turns out there's all the difference in the world because this kind of mathematics allows us to solve incredibly hard problems. Okay? And it's based on the fact that having a divergent series is no problem at all. In fact, we're going to learn that divergent series converge to the answers, converge to the things that they represent, much faster than convergent series. Generally, we're kind of disappointed if we get a series like this that converges. Okay? It's much better and faster if the series diverges because we can extract the answer far more efficiently and far more rapidly. Okay? I'm trying to entice you into this course. Okay. Okay, so let's look at a slightly different way of solving that problem, because I think this will emphasize what's going on. Someone else comes across this problem here. Okay, someone else discovers this problem, and they have just taken a course in quantum field theory. So they say, look, I've learned all about weak coupling expansions, and Feynman diagrams, and things like this. So I'm not going to put the epsilon over here. I'm going to put the epsilon over here. Seems like a perfectly reasonable way to approach the problem. So step 1, I'm going to solve the problem epsilon x to the 5 plus x equals 1. Okay? Why did I choose to insert epsilon over here? Because once again, when epsilon is equal to 0, the unperturbed problem is really easy to solve. In fact, when epsilon is equal to 0, the unperturbed problem becomes x equals 1. Okay? And the solution to that problem is x equals 1. Okay? That sounds pretty good. Great. So now, let's do perturbation theory. Okay? Let's assume that the answer, x, as a function of epsilon, has the form 1 plus a epsilon plus b epsilon squared, and so on. And we plug it into this problem, okay? And let's see what happens. First of all, we've already raised, we already know what happens when you raise x to the 5th power. But now things are going to be a little bit simpler because this thing is going to be multiplied by epsilon. So we don't need, if we're going to work to, say, order epsilon squared, we don't need so many terms. Let's see, we don't need this term because all this is going to be multiplied by epsilon, right? So when we do perturbation theory, we have epsilon times 1 plus 5a epsilon plus epsilon squared times 5b plus 10a squared. Okay, there's the epsilon times x to the 5 term. Okay, and then there is a x term, which is 1 plus a epsilon plus b epsilon squared plus c epsilon cubed. Okay, and so on. And all this has to be equal to 1. Okay? Now, you know what we do next. We have to look at the coefficients of like powers of epsilon. So epsilon to the 0, the coefficient of epsilon to the 0 on the left is 1 and on the right is 1, so the equation becomes 1 equals 1. And that had to work because this is the unperturbed problem. We've already solved the unperturbed problem, so this is merely, telling us we haven't made a mistake yet. Okay? And here's the epsilon to the 1st power. So let's see, there's one term over here, which is just 1. That's epsilon squared, epsilon cubed. Here's an a epsilon, 1 plus a is equal to 0. Good. Okay, that's the next equation to solve. The epsilon squared equation reads from here, there's 5a, and from here, there's a b, and that's equal to 0. These equations actually look simpler than the previous equations. Okay? And epsilon cubed, what about that? Let's see. This says 5b plus 10a squared. Okay? So there's an epsilon cubed term. Here's 1. Plus c is equal to 0. And so here are the equations. They're pretty simple. So let's see. The solution to this equation is a equals minus 1. Okay? You put in minus 1 here, and you get, what's b? 5. Okay, so b is equal to 5. Now we go to this equation, okay? And 5 times 5 is 25 plus 10, a squared. A squared is 1. Plus c equals 0, so c is equal to minus 35. Okay? So now the perturbation series looks like this. If you plug into the perturbation series, we know that x of epsilon is 1 minus epsilon plus 5 epsilon squared minus 35 epsilon cubed, and so on. Okay. Now we get to the last step, the 3rd step of the problem. So we're done with step 2. Step 3 is we set epsilon equals 1 and we sum the series. So our first approximation is 1. And if we take 2 terms in the series, we get 0. And if we take 3 terms in the series, we get 0 plus 5. Okay, and if we take 4 terms in the series, you get 5 minus 35. It's minus 30. And so on. Not quite as effective as before, apparently. And so let me just show you what happens. If you continue with the work and you put an epsilon over here, this is what I call a weak coupling approximation, and you work out the perturbation series, this is what the perturbation series looks like. And once again, by the way, if you like interesting problems, you can, just by staring at these numbers, that's the best way to do it. by the way. I don't know a better way to do it. You can stare at these numbers, and if you work at it for a while, you'll find a formula. There's a simple closed formula for these numbers. Now, if you try to sum the series at, I wrote x equals 1, but I mean epsilon equals 1, the radius of convergence of the series is 0.08. And you're plugging in epsilon equals 1. So it looks like we have here a disaster if you just take this series just up to this point and you plug in epsilon equals 1. The prediction is that x of 1 is 21,476, which is not a good approximation to 0.755. Not really a very good approximation. And this is the problem in quantum field theory, okay, which, if we have time, we will talk about it in the course, okay? So in quantum field theory, this is exactly what happens. In fact, in general, in quantum mechanics, not just quantum field theory, it is a fraud because in a standard quantum mechanics course, you are taught perturbation theory. Okay, that's usually during the sleepy part of the course, towards the end of the second term when everybody is bored. You're taught perturbation theory, and that's it. Okay? And you think that you know how to solve problems. And that is garbage, because almost always, if you pick a series out of a hat, it will be a divergent series. It is rare and unusual for a series to converge. However, we are delighted when we see a divergent series like this. And that is because there are powerful, although not completely rigorous, techniques in mathematics that you can use to sum this series and get an arbitrarily accurate finite answer. And not this answer, of course, but the answer 0.755. Okay, and I'm going to be teaching you those techniques. It's hard to believe that you can sum a divergent series and get a finite answer, a meaningful finite answer, but you can. One such technique is called Padé summation, and we're going to talk about that. But there are lots of techniques, such as Borel summation, that we're going to learn. Okay, so we need to learn how to sum a series. Okay. And one thing that I will be teaching you in this course is how to sum a series if it converges. Because the general rule is that if you are given a series and you have to add it up, the dumbest thing that you can possibly do is add it up. Okay? If you need to find the sum of a series, the worst possible technique is to add the numbers in the series together one at a time. It's a terrible idea. There are much better ways of summing a series. Okay? And if the series diverges, it's not only a stupid idea, it doesn't work. Because if the series diverges, you know what the answer is. It's infinity. Okay? So this is the outline of the course. I was thinking about how to organize the material in this course. And this is what I came up with on the airplane. I hope it works. What do you think?
Yeah, it worked the last 2 times.
It worked. Okay, so we'll try it again. So basically, this is the beginning of what I will be talking about. I will first show you how to sum a convergent series. We're going to spend a day talking about things like that. I will then show you how to sum a divergent series, and we will apply it to various interesting series that we get solving hard problems. And what I want to do in this course mainly is to teach you some once you know how to sum perturbation series, teaching perturbation theory is no longer a fraud because it's something that you can really use. Okay, when you get a divergent series, you're going to learn what to do with that series. And I would like to teach you some very, very fancy techniques, perturbative techniques. I'd like to teach you boundary layer theory, which is a very powerful technique for solving very difficult differential equations. And boundary layer theory, in fact, is a special case of an even more powerful perturbation theory called WKB. WKB, how many of you have seen WKB or heard it talked about? Good. Okay. I doubt that you've seen it done correctly. It's a technique that is usually just run over very, very quickly, but it is an incredibly beautiful idea. And I would like to talk about that. And depending on how strong you are, maybe we'll do lots more. Who knows? Maybe we'll do multiple scale perturbation theory, which includes WKB as a special case. We'll just have to see how interested you are and how fast we can go. Okay. The Shanks transform is what I'm going to be talking about next time, and I don't want to begin talking about it now. The Shanks transform is a technique that we're going to use to solve convergent series. Okay? But before we get to some of these techniques, what I want to do is talk a little bit more about this problem, because I want to find out why it is that this problem is this seems to be a really nice problem, the way we solved it over here. And the way we solved it over here, it wasn't such a nice problem. Okay, it seemed to give us difficulties. Can you tell me why that is? Why is it that solving the problem this way didn't seem to be so effective, at least at a naive level? It gave rise to a divergent series. Why is it that this method wasn't as useful, superficially at least, as this method? What was the difference? Why is putting an epsilon over here different from putting an epsilon over here? In this case, we put the epsilon over here. In the second case, we put the epsilon in front of the x to the 5 term. What's the difference? Why is there a difference? Yeah.
Something about the number of roots changing with epsilon.
Very, very, very good. Excellent.
Because there you have one root and then suddenly you have 5
Excellent.
roots. There you have
Excellent. You're absolutely right. Okay? So there's a difference. In this problem, we put an epsilon into the problem in such a way that nothing abrupt happened at epsilon equals 0. That is, as you go down to the unperturbed problem, there were always 5 roots. But something very strange happened over here. When epsilon was equal to 0, there's only 1 root and not 5 roots. So the question is, where'd the other 4 roots go? Okay? So I would like to ask, can we solve this problem approximately? We can't solve this problem exactly, but can we solve this problem approximately when epsilon is approaching 0? Now, we don't know the mathematics for doing this. Okay? Of course, we would know the mathematics if we had a quintic formula, but we don't have a quintic formula. So I need to teach you new mathematics. Okay, and that's the next step. So let's begin by talking a little bit about asymptotics. Okay. So I want to introduce, this is a very beautiful and a very subtle idea, and I'm just going to give you a superficial introduction to the notion of asymptotics. Okay, and remember, asymptotics is, in fact, when I explain this to classes that I teach, I say, the first amazing breakthrough in mathematics you saw, I guess, when you were in elementary school, and you learned this symbol, okay? And then you learned, and from there you learned exact mathematics. And what you learned is that whatever you do to the left side of this equation, you have to do to the right side of this equation, and it remains an equation, okay? And the word equal and equation are the same, okay? What we're going to do is we're going to replace this symbol by this symbol. Now, this symbol, if you see this symbol is read is asymptotic to. This symbol means is equal to. This symbol means is asymptotic to. Let me tell you what this symbol isn't. This symbol, don't make a mistake. There are a lot of symbols that are written down by sloppy mathematicians, or maybe there aren't any sloppy mathematicians, but sloppy physicists. You know, you see things like this. Have you seen that symbol? Or maybe this symbol? Or, I don't know. You've seen various. Forget these symbols. These are ridiculous symbols. I mean, you've seen. I think this symbol means is approximately equal to, but I don't know what that means. Is approximately equal to. Is 3 approximately equal to 4? That's a ridiculous question. Of course it isn't. 3 is 3, 4 is 4. Of course, it is true that the square root of 3 approaches 2 for large values of 3. Okay. But in general, 3 is not equal to 4. It's also not true that 99 is approximately 100, because it isn't. 99 is 99, 100 is 100. They're different. So, you know, you could try to introduce fuzzy thinking into mathematics and say 99 is very much like 100, but it isn't. Okay, and this symbol here is a very precise symbol. Okay, so what I want to define for you is what it means to say that f of x is asymptotic to g of x. Okay, and it turns out already this is not a correct statement of anything. Okay, this doesn't mean anything. Okay, or it's an incomplete statement. It's like the sentence that reads, the rest of this sentence is written on a rock in. Okay, this is an incomplete sentence. So, an asymptotic approximation, okay, or this is an asymptotic relation, okay, must be associated with a limit. And a correct statement would read, f of x is asymptotic to g of x as x approaches x naught. Okay, and I don't have to write as. Okay, this is a correct statement. And let me tell you what this means. It means that the limit as x approaches x naught of f of x over g of x is 1. That's what it means. Okay, so let's write down a few asymptotic approximations or asymptotic relations. Sine of x is asymptotic to x as x goes to 0. Is that true or not? Okay? And by the way, and let's write another one. E to the x is asymptotic to 1 as x goes to 0. Is that true? You notice something very interesting happening. This is a rather complicated function. And this is quite a simple function. Okay? Same here. This is a rather complicated function. This is quite a simple function. Asymptotics is a way of replacing very complicated functions, like Bessel functions, or functions that don't even have names, by functions that do have names and that are very simple. So asymptotics is a way of simplifying mathematics that's very, very, very complicated. Okay? So this is a correct statement. How about the equation x cubed is asymptotic to 0 as x goes to 0? You say, no, that's right. This is a completely wrong statement. So let's remember that nothing is ever asymptotic to 0. You can never say that something is asymptotic to 0. Okay? Nothing is asymptotic to 0. of course, x cubed is very, very small as x approaches 0. But the best that I can say is that x cubed is asymptotic to x cubed as x goes to 0, because I don't know a simpler way of writing this. Of course, I could write it in a more complicated way. I could say x cubed is asymptotic to x cubed plus x to the 4th as x goes to 0. That's true. Okay. But if I'm trying to put a simpler thing on the right-hand side, I don't know a simpler thing. So remember that nothing is asymptotic to 0, ever. Nothing is ever asymptotic to 0.
Oh, if you want something simple, could you not put x?
What's that?
You could put x cubed is equal to x.
Is asymptotic to x? No, it isn't.
Now, as x goes to 0.
No, it's not true. X cubed is not asymptotic to x as x goes to 0.
Oh, yeah.
Okay, because the ratio of x cubed over x either approaches infinity or 0, but not 1. Okay, so this is a quick definition of the asymptotic symbol, and there are 2 different asymptotic symbols we're going to use in class. One of them is this symbol here, but there's another symbol that's also very useful, and that's this symbol. Okay, and this symbol is read is negligible compared with. Okay, so for example, x is negligible compared with 1 as x goes to 0. Okay, don't make a mistake, by the way. This doesn't mean less than, and it doesn't mean much less than. It doesn't mean that. Okay, because less than is an ordering relation. You know, positive, negative, you know, -1 is less than +1. Okay? So, for example, x is, say, x squared is, or let's say minus x squared is less than 1. That's certainly true, okay, if x is real. Certainly less than 1. But 1 is negligible compared with x squared, or minus x squared, okay, as x goes to infinity. So what does negligible compared with mean? It means when you say f of x is negligible compared with g of x as x approaches x naught. What this means is that the limit as x approaches x naught of f of x over g of x is 0. So over here, that limit is 1. So they're approaching each other. Okay. Over here, f is becoming negligible compared with the other because this ratio is going to 0. You understand? That's a quick dose of asymptotics. Okay. So let's see how you would use asymptotics to understand a problem. Because, good, time is going to be right. Good. Okay. So you pointed out that what we did over there was we lost some roots. And the question is, where did the other roots go? Where are they? Okay, we lost 4 out of the 5 roots. Where'd they go? They just disappeared out of the universe or something like that? Where'd they go? So to understand where those roots went, let's go back and think let's go back and think about what we did in this problem as we approached the unperturbed problem here. Okay, that's the question that we'd like to think about. All right, so let's try to understand the problem x to the 5 plus x equals 1 when you put an epsilon in front of here, and when we examine this problem in the limit as epsilon goes to 0. what happens? Okay. Now, asymptotics is fantastic because problems that you cannot solve exactly, problems that you cannot solve when they contain an equal sign, suddenly become very easy to solve when you have an asymptotic sign. Okay? So how do you solve such a problem? Well, you notice that there are three numbers in this equation. Okay? In fact, let's make a general statement before we approach that. Suppose I have an equation that says f of x plus g of x equals h of x. Suppose you have such an equation. Okay? And suppose g of x is negligible compared with f of x as x approaches x naught. Suppose that's true. Okay? What can you then say? I heard you say it exactly right. Somebody whispered it. But
F is asymptotic to H.
exactly. If f of x is negligible compared with g as x approaches x naught, then, okay, let's say, if this is true, then I can throw away f of x and I can conclude that g of x is asymptotic to h of x as x approaches x naught. That's the connection.
The F of X. No.
Sorry? Oh, I'm sorry. That f of x is asymptotic to h. G is negligible. So f is asymptotic to h of x as x approaches x naught. Okay? So this is the connection between this symbol over here and this symbol over here. The asymptotic symbol and the negligible symbol. Okay? So great. Here we have an equation with three terms in it. And we're considering what happens as epsilon goes to 0. Now, I think let's make more space here. Now, typically, not always, but typically, what happens in a situation like this, where we have an asymptotic limit, typically what happens is that one term becomes negligible, and the other two terms become asymptotic to one another. Now, it could be that all three terms are exactly the same size. But what's the chance of that? Okay, if you pick three numbers out of a hat, can all three numbers be the same size? Nah, very small chance. Okay, of course we have to consider that, but there's only a very small likelihood of that. So how do you solve, or how do you even attack such a hard problem as this? Well, we're going to use the method of dominant balance. Okay. The method of dominant balance consists of saying it's likely that one of these two terms becomes negligible, and the other two terms are now asymptotic to one another. Well, which term becomes negligible? Well, there are three possibilities. The first possibility is that 1 becomes negligible. We can throw away 1. And that epsilon x to the 5 would now be, plus x would be asymptotic to 0. Oh, wait a minute. Excuse me. Nothing is asymptotic to 0. So let's be more careful. If we can throw away 1, then it must be that epsilon x to the 5 is asymptotic to minus x. That's one possibility. We don't know if that's a correct possibility. A second possibility is maybe we can throw away x. Maybe x is the thing that's negligible in this equation, in which case epsilon x to the 5 would be asymptotic to 1. This is in the limit as epsilon goes to 0. And this is as epsilon goes to 0. And a third possible statement would be, so we've thrown away 1, we've thrown away x, maybe epsilon x to the 5 is negligible, okay? And we conclude that x is asymptotic to 1 as epsilon goes to 0. So let's look at each of these statements in turn and see if any of these are correct. Okay? We don't know which of these might be correct. Let's see. What about this one? Is this a correct statement? Well, asymptotics is self-referential. Do you like self-referential statements? It's very hard to prove things with asymptotics, but it's very easy to verify things. Okay? So take this statement. If it's true that epsilon x to the 5 is negligible, then it must be true that x is asymptotic to 1 as epsilon goes to 0. Could x be asymptotic to 1 as epsilon goes to 0? If it is, would it then be true that epsilon x to the 5 would be negligible? Sure, because epsilon is going to 0. If x is asymptotic to 1, that means it's very close to 1. You raise it to the 5th power, you multiply it by epsilon. Can we neglect this compared with the other two terms in the equation? Yes, this is perfectly valid. Okay? In fact, that is true about what we wrote down here. Okay? In fact, there is a root that is very near 1. Okay? In fact, it's 3/4. That's quite near 1. Okay, so this is okay. There's nothing wrong with this. But we didn't learn anything we didn't know. What about this? Well, asymptotic equations are like ordinary equations, equations with equal signs, in the sense that you can generally do the same thing to both sides of the equation, and it still remains asymptotic. So for example, I have an asymptotic equation here. How would I solve this equation? Well, I begin by dividing by epsilon. X to the 5 is asymptotic to 1 over epsilon as epsilon goes to 0. Take the 5th root. So x is asymptotic to 1 over epsilon to the 1/5 as epsilon goes to 0. Okay? And by the way, when I take the 5th root, there are 5 possible roots I get here. I really shouldn't write 1. I should write omega, where omega is one of the 5th roots of 1. You know some complex variables. What are the 5th roots of 1? What would omega be?
E to the power of
E to the 2 pi I over 5, or e to the 4 pi I over 5, and so on. Those are the 5th roots of 1. Okay, so omega is a complex number, and when you raise it to the 5th power, you get 1. So this is the solution to this equation. That's the asymptotic solution to this equation. Now, was it valid to throw away x? Well, as epsilon goes to 0, you could see that x is blowing up, right? Because there's an epsilon to the 1/5 in the denominator. You all see that? So we looked at this equation and we said, throw away x. Okay, that's what we said, throw away x. Keep these two terms. So for example, we kept the term 1 and we threw away x. But you notice that x is gigantic. It's blowing up. It's going to infinity as epsilon goes to 0. And we threw it away, and we kept 1. Was that valid? No, it's not valid. Contradiction. Okay? So asymptotics is self-correcting. It says you made a wrong assumption. Well, there's only one remaining possibility, and I sure hope this is going to be it. Okay? Now, if x is not equal to 0, we can divide both sides of this equation, this asymptotic approximation, by x. And we get epsilon x to the 4 is asymptotic to -1 as epsilon goes to 0. And now what do we do with this? This is an asymptotic equation, or an asymptotic relation. Okay? Let's divide by epsilon. X to the 4 is asymptotic to minus 1 over epsilon as epsilon goes to 0. Now let's take the fourth root. X is asymptotic to minus 1 over epsilon to the 1/4 as epsilon goes to 0. But it's not really 1 here, right? It's one of the fourth roots of 1, or of minus 1. Okay, so I'll write here omega, where omega to the 4th is equal to minus 1. One of the 4 roots of minus 1. Okay, now what did we do here? We threw away 1, but we kept x and epsilon x to the 5. Was that valid? Yes. It is true that 1 is negligible compared with x, okay, which is of order, 1 over epsilon to the 1/4. This is a valid equation as epsilon goes to 0. Okay? That's perfectly okay. Therefore, now we know that x has this form. And now we know what happened to the other 4 roots. We have just calculated approximately, using asymptotics, the other 4 roots. And we know we know the solution to this puzzle. Where did the other 4 roots go? The other 4 roots, these are the 4 roots of minus 1. The 4 roots of minus 1 are distributed in the complex plane like this, okay? And the distance from the origin in the complex plane is going to infinity, right? It's going like 1 over epsilon to the 1/4. So the other 4 roots went off to infinity like this. That's where they went. Okay? Do you see that we have cracked into this very, very hard problem by replacing the equal sign by the approximation sign, the asymptotic approximation sign? Okay? And in fact, this is just the first approximation. We can develop an entire series where this is the first term, okay? And we can find more and more and more precise approximations of the roots of this polynomial equation. We can find arbitrarily accurate calculations of the solution to this approximate equation. Arbitrarily accurate. There is no limit to the amount of accuracy. So if you walk into the room and you say, I demand 15 decimal places accuracy, I can give you 15 decimal places. Okay? And if you walk in and you say, no, I want 30 decimal places accuracy, I can give you 30. No problem. Okay? But I can never tell you what the answer is equal to. That's impossible, because this is not a solvable problem. Okay? So I want to emphasize in this course that there's a giant gulf between an exact approximation, okay, an exact solution, that is, or an arbitrarily accurate approximation. Okay? Now, let's see. Oh, perfect. Oh, all right. Okay, so let's stop here. Next time, I want to show you that the mathematics that I've taught you is so powerful that we can solve problems like that in a few minutes, essentially in under a minute, that you have been told your entire life are absolutely insolvable problems. Cannot be solved. Okay, and we'll just do it just like that. What's an example of an infinitely hard problem? How about a Schrodinger equation? Okay? Nobody knows how to solve a Schrodinger equation. When you take quantum mechanics, you learn the harmonic oscillator and you learn the hydrogen atom, and then you give up. Because there really aren't any other Schrodinger equations you can solve. No, that's not true. We're going to solve them all.
I was thinking more along the lines of QCD.
Yeah, we can. The next step is QCD. We'll just. Okay. Are there questions before we quit? Or comments? Or something?
I'm sorry.
Yeah,
I haven't recognized the word method of what balance.
you haven't.
Method.
Dominant balance.
Dominant. Yes, dominant. This word is dominant balance. Okay. What I mean by dominant, okay, is that all of the terms in the equation dominate over one term in the equation. Okay, so here we have an equation containing 3 terms, and 2 of these terms dominate over the 3rd term. And what we found is that this is the correct answer. What we found is that this term and this term are big, and this term is negligible. So these 2 terms here dominate over that term. But if this term is thrown away, because it's unimportant, then these 2 terms have to be balancing each other, because this very big term and this very big term have to almost cancel each other, because this term is negligible. You see? But it's fantastic, because you see, we don't know how to solve an equation with 3 terms in it, but we do know how to solve an equation with just 2 terms. Okay? So asymptotics allows us to simplify equations. We, for example, in this course, will never need to use the quadratic equation, because asymptotics says that you don't need to solve a 3-term equation. You can always replace it by a 2-term equation, which doesn't require that you remember anything. Okay? So asymptotics is a fantastically powerful and wonderful mathematical tool. If you don't know asymptotics, basically you are reduced to just sitting in front of a computer and generating numerical solutions to problems. And this course is about generating analytical solutions. Okay? Yes?
I'm a bit confused. Like in this kind of perturbation theory, we introduce small parameter,
Yes.
and then make series, then set it to unity. But for example, in quantum mechanics, it's true. We usually like have a small parameter,
We
which
do?
we don't set to unity like in the end. So it's like parameter in the problem.
Okay, so now the parameter you're referring to here is,
No, for
H bar.
example, some relation of 2 like physical
Well,
values in which you.
okay, so we are going to talk about this in great detail. And this is what this course is going to be about. Often, we treat h bar as being small. But you and I know that h bar is not small. It's equal to 1. Okay? Because it depends, h bar is a number that contains units. So depending on what system of units you choose, h bar may be gigantic or it may be small. You can't say that h bar is a small number or a big number. In MKS units, yeah, it's 10 to the minus 34, but that's not a small number because it contains dimensions which make that number either big or small. Okay? But it's often very, very powerful to think of h bar as being a small number. And we have to make that precise, which we will. And when you do, that is where WKB theory comes from. Okay, that's where WKB comes from. If you treat other numbers in quantum mechanics as being small, then you are doing other kinds of perturbation theory, and we're going to do that. We're going to investigate that in great detail. Okay, so that's the objective of this course, is to take a very fancy equation like the Schrodinger equation and try to find a small parameter, try to find it and treat it consistently and through perturbation theory and so on. That's what we're going to do. Okay. This is a very subtle problem and a very interesting problem. One of the things that you're going to learn along the way is why it is that quantum mechanics is quantized. You know, why are energy levels discrete? Perturbation theory will explain that to us. Okay, any other questions? Okay, well, I hope I've gotten you interested in the idea that